Okay, now we're at 11:29. So in 1 minute, we are live now. So
welcome to RSC Bio Solutions overview of environmentally acceptable lubricants, also known as EALs. My name is George Cook. With more than 35 years in the chemical industry in sales, R&D, and technical service, I currently focus on formulation development and field technical service in lubricants and cleaners at RSC Bio and will serve as the moderator for today's webinar. I would like to introduce today's presenter, Dr. Larry Beaver, Vice President of R&D for RSC Bio Solutions, where he oversees innovation, development, and regulatory functions for the Envirologic and Futera product lines. For over 30 years, Dr. Beaver has been actively involved in the commercialization of safer consumer and industrial chemical products. His current research efforts focus on VGP-compliant cleaners, gear oils, greases, and hydraulic fluids for land and marine applications. Dr. Beaver is the principal inventor of more than 14 patents. He is an active member of STLE and NLGI and currently serves on the Industry Advisory Board for the Tribology minor in the College of Engineering at Auburn University. We look forward to taking your questions at the end of the webinar presentation. Please use the Q&A function inside Teams to submit your questions, and we'll take them on a first come, first served basis.
thank you, George. Appreciate the introduction. Today we're going to talk about EALs, and that's an acronym for environmentally acceptable lubricants. Now, it's only been fairly recently in the United States that there has been an accepted definition of an EAL. So we're going to spend time today talking in three different areas. One is, what is an EAL? What's an environmentally acceptable lubricant? Why would you consider an environmentally acceptable lubricant, an EAL, to replace a conventional lubricant, hydraulic oil, gear oil, or grease? And how do EALs perform both compared to each other and compared to the mineral oil formulas that they replace? There have been definitions of environmentally acceptable products in use, particularly in Europe, for quite a number of years. Blue Angel, Swedish Standard, Ecolabel have criteria for what's considered environmentally acceptable. In the United States, it's only been recently, in 2013, when the US EPA published their vessel general permit, that an EAL has been clearly codified, or what the requirements for an EAL are. The vessel general permit sets the requirements for operating shipping vessels over a certain size. I think it's 79 feet in the United States, and so this applies to any ship coming in of that size or larger coming into a U.S. port. And the U.S. EPA vessel general permit in 2013 specified that to be considered an environmentally acceptable lubricant, a lubricant that would be a hydraulic fluid, a gear oil, or grease, would need to be readily biodegradable, that is specified in the VGP as greater than 60% biodegradability in 28 days in standardized testing. The lubricant had to be minimally toxic, and those requirements are set forth in the VGP as measured by impact on several aquatic organisms. And third, an EAL can't be bioaccumulative, which means it can't build up in the tissues of marine life. So starting in 2013, we in the United States had a clarification of what constitutes an EAL, and this also drove the business, the marine business, the shipping business, to begin converting to EALs for ships coming into U.S. ports. So we'll talk a little bit about the types of EALs, and what we're going to use here is a an illustration, if you will, or a codification of EALs, hydraulic fluid EALs, in the ISO standard. Now keep in mind that EALs are more than hydraulic fluid. EALs, in this case, we'll be discussing hydraulic fluids as they exemplify, if you will, the different types of EALs. But the EAL is characterized, generally speaking, by the chemical composition of the base oil, not the additives, not the thickeners. The chemical composition of the base oil is generally understood by tribologists to have a primary effect on the ability of the lubricant to do its job. In this case, the base oil is generally, but not always, the primary factor associated with how rapidly the product biodegrades and how little it bioaccumulates. So we talk about different types of base oils and different types of lubricants derived from those base oils. So we'll talk about 4 different EALs. These are the 4 recognized by ISO. The first are triglycerides, that is HETG, that's a nomenclature in the ISO standard. The H stands for hydraulic fluid, the E stands for environmental, and the TG stands for triglyceride. The next are the HEPGs, once again, hydraulic fluid, environmental, and PG stands for polyalkylene glycol. These are also known as PAGs. The third category are the synthetic esters. That's HEES, hydraulic fluid, environmental, ester, synthetic. The last category is HEPR, and when it was originally codified, it was listed as a hydraulic fluid, environmental, polyalpha olefin, and related. Now it's known as polyalpha olefin and synthetic hydrocarbons in the standard. So those are the 4 main categories, and there are variations on a theme. You can have different triglycerides, different polyglycols, different synthetic esters, and different HEPR hydrocarbon technologies, but these are the 4 basic clumps, 4 basic types of EALs. So let's talk a little bit about each one. This is a graphic depiction allowing you to compare them with respect to oxidation resistance, water resistance, lubricity, and seal compatibility. So we'll start with the triglycerides, the HETG category. These are conventional vegetable oils, often called seed crop oils. They include soybean oil, high oleic soybean oil, canola oil, sunflower oil, safflower oil, basically all the oils that you would think of when you think of a food type of seed crop oil. They have both ester functionality and double bonds in their backbones because they are what are called fatty acid triglycerides. So they have a propensity to both oxidize and hydrolyze. And hydrolysis is the reaction between an ester and water, and that limits their lifetime. They break down readily in the presence of oxygen and water, and the upside to that is they are also very rapidly biodegradable for that reason. They have excellent lubricity. They have a high viscosity index, which makes them more efficient across a broad temperature range. They're compatible with many, but not all seal types used in hydraulic systems. And they have a history of use in construction and work trucks. A lot of garbage trucks, for instance, used HETG triglyceride-based hydraulic fluids. And they do offer, generally speaking, a cost advantage over the other EAL options, and that cost advantage is balanced out by the lower lifetime and more frequent change-out intervals, typically for the triglyceride hydraulic fluids. Next category are the polyalkylene glycol hydraulic fluids. These are generally synthetic, not usually bio-based. They have fairly good oxidative stability, fair to good lubricity. And when I say fair to good, this is a a type of hydraulic fluid that can have a very wide range of performance based on how carefully the organic chemists put the backbone together. The HEPG category is typically incompatible with conventional seals and filters. And HEPGs, the PAGs, are typically hydrophilic, which means they love water, and so much so that some of them are fully miscible with water. In other words, once water gets into the system, it can't be separated out. PAGs are also incompatible with other lubricants, so that makes it very difficult to do conversions without tear down and rinsing. The main claim to fame to the PAGs is they are incredibly fire resistant, which means that they are often used in military vessels for that reason. The third category are the synthetic esters. Now think of a synthetic ester as a triglyceride on steroids. You take a triglyceride, you tear it apart, and you put it back together again, and you get rid of some of the double bonds, and you've got a very high performance synthetic ester. Now, unfortunately, synthetic esters, while they are either fully synthetic or bio-based, they still have ester functionality in them. So hydrolysis at the ester functionality is still an issue, and there are still oxidation issues associated with the synthetic ester. So saturating esters can improve oxidative stability, but they don't eliminate the hydrolysis step. They typically have excellent lubricity and excellent viscosity index, but often, if not always, synthetic esters require special fluoroelastomer seals. So if you're converting a system from mineral oil to ester, you will often have to change your seals in that system. The last category is the category HEPR, which is the PAO and synthetic hydrocarbon category. These can be either bio-based or fully synthetic hydrocarbon-based oils. So you can use a fully synthetic product that has very little bio-based content, or you can use a HEPR kind of backbone that has bio-based carbon in it. So there's a wide range of renewability options associated with this category. Now, the hydrolysis and oxidation of the HEPR type base oils can easily meet or exceed that of mineral oil products. They have excellent lubricity and viscosity index, and they have a very wide compatibility with seal materials, HNBR, NBR, FKM, and polyurethane. So this category of hydraulic fluids based on the synthetic or biosynthetic hydrocarbon base oils is the only one of the four that has true drop-in compatibility with conventional mineral oil-based fluids. So if you have a piece of equipment running mineral oil, you don't have to make major changes during the conversion, because these HEPR type hydraulic fluids typically have very good miscibility and compatibility with others in the system, with the exception of the polyalkylene glycol type hydraulic fluids, which don't work and play well at all with any of the other categories. So these are the kind of things that you think of when you look at those four categories. And here's some of the typical problems that you can have with a hydraulic fluid. Foaming is a very bad thing. Foaming negatively impacts a hydraulic fluid's operation in a system, and sometimes to the extent that it makes a piece of equipment unsafe if it has a great deal of foaming in it. Emulsification can also be an issue. Typically, you want to separate water out of a system and not emulsify it. And also separation and instability. You want to make sure that your technology you're using is stable and doesn't separate or phase out over time. So let's talk a little bit about foaming. Here's an example. This is a Futera example, which is our premier, if you will, HEPR technology for hydraulic fluids. And this is a foaming test. And the ASTM D892 foaming test involves bubbling air through a sample of the hydraulic fluid and measuring the amount of foam that's formed. And the first number in each data set is the amount of foam that's formed. And then you wait 10 minutes, and that second number is how much foam remains at the end of 10 minutes. So an ideal case would be 0, 0, which you see here with the HEPR, which is our Futera. In sequence run 1, run at 25C, we had a 0, 0 number. You run the test again, same fluid, no change, at 92C. So you warm it up and you run it again to see if there's more foam generated at 92C. And then you cool it off and run it again to see if anything in the formula has chemically changed, or in the defoamer package is chemically changed by the heat. So if you make it through this sequence and the numbers don't dramatically differ from the beginning, phase 1 to phase 3, you've got a pretty stable defoamer package in the system. And of course, you can age a sample and also check it then. But the point I want to make here is that you can see that the hydrocarbon product, the HEPR product, performs as well or better than the petroleum product that it's replacing in the system. Now, why is the foaming or non-foaming characteristics of a hydraulic fluid important? Well, non-foaming means you get less air trapped in the system, less foam carried through the system. That gives better lubrication. Foaming and air entrainment can inhibit film strength in the lubricant and can cause cavitation in pumps, for instance, so better pump life as a result. And the last thing you want is foam in a system that can cause bad operating characteristics, if you will, in hydraulic braking systems or in lifting systems. Foaming and air entrainment can cause sponginess and failure in the system. So the lack of foam is more than just a convenience, it's a necessity. So let's talk about some of the other characteristics of HEPRs versus or among the EALs, not just HEPRs versus, but just how do the EALs compare. The first chart here on the left is the rotating pressure vessel oxidation test results, and the minutes, the higher the minutes, the more stable the product is to oxidation. And as you can well imagine, you look at the HETG at the bottom and you get about 100 minutes. The longer it runs before it fails, the better the oxidative stability. The synthetic ester goes 163 minutes. The glycol does pretty well at 800 minutes. And the sample of petroleum hydraulic fluid at the top went 878 minutes. And I would say there can be a very wide variety of numbers in each of these ranges. Okay. We were actually being very gracious to the mineral oil because the one we looked at gave an 878 minute number. It's not unusual to see a more poorly formulated mineral oil based hydraulic fluid come in at 200 or 300 minutes. The real takeaway here is a properly formulated HEPR can be dramatically better than a conventional mineral oil with 1,399 minutes before failure in the oxidation test. That is a dramatic improvement. Likewise, when it comes to demulsing, which is the ability to kick water out, separate water out of a system, you look at Futera down here in the lower right-hand corner of the second graph, and you see that the blue line indicates how long it took to separate the water from the mineral oil or from the HEPR-based hydraulic fluid. And you can see it took 5 minutes to fully separate the oil out, and it was 100% separation. That's an ideal case. The faster you separate it and the more completely you separate it, the easier it is for things like oil water separators or even simply sedimentation of the water and draining out of a storage tank. The easier that is. So compared to petroleum, you can see that the mineral oil-based hydraulic fluid took 10 minutes to fully separate. And so we're at least as good, if not better, than a conventional mineral oil-based hydraulic fluid. And then you see the emulsifiable. This is in here as an example of an emulsifiable ester. At the end of 30 minutes, it was 57.5% demulsed. These two, HEES and HEES2, are just two different ester hydraulic fluids, and you can see at 30 to 35 minutes gave 93 to 100% separation. The glycol, it should be no surprise, gave no separation even at the end of 30 minutes because it was miscible with water. And the triglyceride took 30 minutes to separate from water, but it did so fully. So you can see that the best way to get water out of the system is a hydrophobic, water-hating base oil like a hydrocarbon, in this case a readily biodegradable one. The last slide here, or the last chart here on this slide, is acid generation, and acid generation is indicative of decomposition, so it's kind of a marker, if you will. So as you see acid level go up, total acid number go up in a hydraulic fluid sample, it gives you an idea as to how rapidly the base oil is decomposing. And you can't just start out and measure the initial or the final acid number, which is here in green, because virtually all systems start with some small amount of acid formation that's not due to decomposition. So you want to remove that from the mix, from the calculation. So these blue bars show the type of acid level seen in the triglyceride, the HES1, HES2, HES3. Those are just 3 different hydraulic fluids based on synthetic esters, and you can see that they have differing levels of acidity to start with, and then as the aging takes place, the acid level goes up dramatically for each of the 3. That's in comparison to the Futera hydraulic fluid, which starts out at a relatively low base number of about 0.6 and never goes above 0.7. So there's no real change in acid number from the beginning to the end of the test. So all these lab tests are really cute to talk about, but how does it really pan out in real life? Well, we've got more than 6 years in an offshore drill ship for our HEPR technology, 10 years in a marine polar fleet propulsion system in stern tubes, and we've got material with Transocean, Oceaneering, Diamond Offshore. As far as the marine side of the business goes, we have equipment with Jacobson, Alltech, Versalift, and American pile driving equipment for land-based applications. So we've got a wide variety of HEPR using customers in the marketplace. So this is backed up by things like you see here, which is 7 years, almost 7 years. Now it's more than 7 years in a stern tube, and that there was no viscosity drift in this material at all. So this is very indicative of the kind of stability you see. You know, there was a time when you were giving up something. When you wanted to be more sustainable, you had to give up performance. You had to give up something. Now you don't have to compromise. You can create a safer world and be more sustainable without having to change out your fluid every 6 months because it's decomposing. We are 100% focused on the latest green technologies. This is all we do. RSC Bio was founded based on these technologies. This is all we do. We are not an oil major with a private label green formula bolted onto our portfolio. This is our very reason for being. We've been in the business since the 1980s. We have both triglyceride and HEPR technologies in the market. We understand them and their synthetic ester competitors very well. We have a full line of greases, cleaners, and hydraulic fluids and gear oils and specialty products, and they're all built around these basic principles of biodegradability, minimal aquatic toxicity, no bioaccumulation, no sheen in the water. We are constantly working to bring our renewability content higher and higher in our products. That's why you heard me use the term biohydrocarbon when I talked about our HEPR technologies. We're constantly working to not only increase the biodegradability of our product, but our bio content of our product. As I mentioned, we have hydraulic fluid, gear oils, a variety of specialty fluids from tractor oil to saw guide oil, wire rope lubricating oil, grease, cleaners and disinfectants. Our sister company has recently launched cleansafely.com, which markets our cleaning and disinfecting products. You know, we're a North Carolina-based company. We operate globally, but our product is blended here in the United States. We own this product. We live for this product. So if there's any questions that you have, please feel free to jump in, and any that we don't have time for today, we will try to respond and post separately on our website. And feel free to contact me at the numbers and email address you see on the screen if you want to discuss this further, or if you have additional questions. George, let's go now to any questions that might have come in.
Okay, Larry, thank you. And as Larry mentioned, this webinar will be posted on our website, and we'll be letting everybody know when it is available for viewing. First question. You discussed a lot about HF fluids and gear oils, more HF fluids, but what about the greases?
Well, we have the discussion centered around the hydraulic fluids, because those are the ones that are clearly codified in the ISO standard. So HE, TG, HE, PG, and so on and so forth. They deal with hydraulic fluids, but the basic principle of creating an EAL crosses all lubricant lines. In other words, the same kind of base oil technology that allows you to produce a premium hydraulic fluid EAL is also the same kind of base oil technology that you would use to create a premium gear oil or EAL grease. So while the nomenclature kind of tends to pigeonhole us or focus us in on the hydraulic fluids, you really, when you're talking about HEPR technology, you're talking about a base oil applicable to all lubricants, from hydraulic fluids to gear oils to greases.
Okay, second question, I'll take this one, is why aren't EALs used more in land-based applications? And that answer is twofold, really. One is that unlike the marine space, the land does not have a US EPA directive requiring equipment to utilize an EAL. With that said, there are still spills that happen. A lot of these spills are not cleaned up. Much like the marine space, where ships were leaking oil into the water over the years, you know, the EPA finally got involved and said, okay, we're going to put a stop to this. If they're going to leak oil, at least we're going to make it environmentally acceptable lubricant. The same thing we hope will happen in land-based equipment, but at this time it hasn't. The other factor that tends to sway people to mineral oil-based products is cost. Too many companies look at unit cost as a measure of the cost of ownership of the oil, and there's a lot more factors involved in what goes into owning using a EAL in your equipment. There's such things as costs associated with spills. There's such things as costs associated with negative PR when spills happen. All of these factor into the ownership of cost, but a lot of companies choose to look at just a unit cost. EALs do tend to be a little more expensive than a mineral oil-based product, but overwhelmingly the reason for land-based equipment not using it is the fact that they don't have to. Third question, why do the HEES type products dominate the global offering? Larry?
Well, part of it is timing and availability. The synthetic esters, they first started tinkering with them in the early 1900s, and they were a natural outgrowth of the natural esters, the fatty acids, the fatty things like tallow and that kind of thing. So the synthetic esters got a head start on the other technology. There's also a very wide range, and you can also, if you're looking for renewability content, bio content, it's easier right now to come up with a wide variety of synthetic esters that do that. And up until they made it into the marine segment, many of the synthetic esters would work just fine for many hydraulic applications, for instance. But you get into the wetter or wet and heat, and that's when the hydrolysis and oxidation take place. So part of it is they got a head start because they were there the firstest with the mostest kind of situation. Now that the HEPR technology is catching up and there's a wider variety of biodegradable hydrocarbons available, and the renewable carbon content of those that are available is going up, I think there's going to be much more competition, if you will, between the HEPR class of base oils and the synthetic esters.
Okay, another question. Did you ever make a lifetime monitoring of RSC hydraulic fluid on a land-based application? We sell our hydraulic fluids, principally the HF products, in a variety of land-based applications, from bucket lift trucks to turf care equipment to construction equipment. And we do monitor it at the request of our customers if we do offer oil analysis programs, and that is one thing that we look at. Typically, the changeout intervals on an HF product is about 1 season, about 1 year. And so in that time span, the products perform well, and we look at the health of the oil as far as the total acid number and viscosity, and those things perform very well.
And I would point out that HF product is our triglyceride product.
Correct. And so in answering your question, have we made a lifetime monitoring of it? Yes, we do, within the confines of the season that it is, and that is based on customer request. Another question. What are the RPVOT and demulsification values of Envirologic HF? Your HF, as Larry mentioned, are triglycerides. And these typically, just like the ester products, in an RPVOT, which is the rapid pressure vessel oxidation test, are exposed to extremely high temperatures with water. And what it's measuring is a drop in the pressure, the amount of oxygen within the container. And when it reaches a 25 psi drop, then the test is considered over. Under these conditions, and presence of a copper catalyst as well, the esters, and which of course a triglyceride is, do not perform very well. And those values will range from anywhere from, say, 75 minutes up to some cases 200, but that's about the extent of it. And when, of course, you get up into the HEPRs, and you're really extending it up to well over 1,000 in some cases. For our Futera, for example, we're up around 1,400, and that is just to simply give you kind of a comparison between the technologies of the base fluids and what they will do.
And with respect to demulsing, our HF would be, as far as demulsing characteristics, would be similar to what you saw on that slide. It'd take about 30 to 35 minutes for 100% complete separation of the fluid in the water.
Another question, what types of applications are RSC Bio gearbox oils used for? Larry, do you want to take this one, or me too?
Well, I can jump in, and you can supplement it if I miss something. I think right now our largest market for our gear oils right now is in the shipping industry, and it's in thrusters and propeller systems and that kind of thing. That's the big market. So you're talking about getting into these giant thrusters that are used to maneuver everything from tankers to cruise ships. That's probably one of the most stressful uses for our gear oils, due to the potential for water contamination and the fact that the dry dock schedule is at least every 5 years for those systems.
Okay, and the last question, we'll wrap it up, is what are some typical applications for triglyceride products? Again, triglycerides are really suited for more land-based applications, and so anything, candidly speaking, that uses a hydraulic fluid in a land-based application can utilize a triglyceride product, keeping in mind that the key to a successful use of a triglyceride in land-based equipment is your change-out intervals. So you never want to put a triglyceride into something that's going to be exposed to extremely high temperatures for multiple year change-out intervals, but for seasonal uses such as turf care equipment, bucket trucks, construction equipment, garbage trucks, the list goes on is where we've had successful uses of triglyceride products in this types of equipment.
Oh, and I would point out I think we're also selling triglyceride hydraulic fluid to safety barrier companies that manufacture the rapidly deploying safety barriers and bollards that you see around important facilities now.
I think that wraps up our question and answer period. We thank you for joining us in today's webinar. And again, if you have any follow-up questions, please feel free to reach out to Dr. Beaver. And once again, thank you.
Thank you very much for joining us today, and thank you, George, for moderating the session today.